This video is again about pointers. The focus here will be on pointer arithmetic and how pointers are related to arrays. And of course, you also will see a few features of ABC that I will just introduce by example. Let's first review a few things before I show you the interesting part down here. We have here two local variables in function main. And that means when we enter the function, we can think of these variables as follows. We have one memory location for this variable a of type int. So this is the memory location for a. A is initialized, which is good practice because otherwise, as you know, local variables would have an undefined initial value. But here it's defined and it's 42. Then we have another memory location for this other variable, ptr, which is of course short for pointer. So we also have here ptr, also initialized with the address of a, so we can think of this as follows. ptr points to a, because we basically store the address, whatever the address is, in ptr. Now here you see the output when I run the program on my machine. And you see, for example, that I'm first printing out the size of a. Now that means I'm printing out how many bytes are used for this memory location of a. And in my case, it's 4 bytes. And I guess you have the same size of int. But on Arduino or other platforms, this might be different. Then you also see the address here, represented in hexadecimal, is a quite large number, but let's say if it would be 1024, it means that we also store 1024 in this memory location for ptr. So this number here and this number here will always be the same after we initialize ptr. And again, these numbers might be different on your machine. So it's okay that I'm using here also made up numbers. In the exercises, by the way, you also want to print out the size of ptr. Then you also have something which is actually platform dependent, but I guess on your machine the size of this variable ptr also will be 8 bytes. So think about how to print out here, for example, the size of ptr. Now let's actually come to the interesting part. I'm incrementing here the pointer variable, the ptr variable, which is of course possible because whatever you store in here is just a number. So of course you can increment it. What we would expect now would be the following. If the value stored in here is 1024, we would expect that it's 1025. If we have these numbers here, we would expect that we somehow increment it by 1. And then this representation in hexadecimal somehow should end with D. But what you actually see here is that this value was incremented by 4. Now where on this slide now does this number 4 show up? It's actually the size of A. Now let's look at a different example where I change the type of this variable A and also the type of what ptr points to. And this is what you see on this slide. You now see that this part has changed. The rest is still the same. And here we actually see a new type for a variable, a character type. And the size of a character type is 1. It's always 1 byte. And that means we again can visualize the situation when we enter function main as follows. We have one memory location for variable a. It's again initialized with 42. Now here the size of this box is 1. Only one memory cell is used for variable a. Then we have this other variable ptr, so another box. It's again initialized with the address of a. So it's pointing to that. You see the numbers here have changed. But again, we could assume that for simplicity, this address is again 1024. then we would have stored the same value again in here. Now again, also print out the size of PTR, and then you should see you get the same size as before, which kind of makes sense. I mean, a pointer is just storing the address of a variable, and it doesn't matter how many bytes this variable requires. It just matters how many bits or how many bytes you need to represent an address. And because I'm using a 64-bit machine, every address is represented with 64 bits or 8 bytes. So this size never should change, no matter to what a pointer is pointing to. But what changes is when you increment this variable, you now actually see that the following happens. We just increment the pointer by 1. So if we would have the address 1024, the pointer afterwards would be 1025. And here, when you look at the actual numbers, you see the same. You also increment it by 1. So the hypothesis is that the amount by which this pointer gets incremented depends on the width of this box. So why can it be a useful thing that sometimes a pointer gets actually incremented by 1, if it's, for example, pointing to a character which has the size of 1 byte, or in other cases by 4, if it's pointing to an integer, where an integer has the size of 4 byte. For that, I want to consider this example, where we have an array and a pointer to an integer. And here I also want to introduce a new feature, this initializer list for an array. Let's begin with that. And for that, I again want to visualize things in memory. The situation when we entered function main, we have two local variables. Variable A is an array with 3 integers. So let's say this is the memory location for variable A. And here I actually want to look at the elements of this array. So let's divide this memory location for array A into 3 memory locations for the 3 elements. So this would be the memory location for the first element, this here for the second, and this here for the third. With this initializer list, you can specify the initial values of these elements. And the important thing is that always all elements get initialized. Even if, like here, we have fewer elements that we specify than we have elements in the array in total. Here we specify that the first element should be initialized with 65. So we have here a 65. The second with 66. And the rest gets filled up by the compiler, or the compiler generates code for initializing the remaining elements, and they will all be 0 initialized. So it's guaranteed that this third element has an initial value of 0. And this also works if you increase the dimension of this array. If you change it to 5, then the compiler will initialize the remaining, or these additional 2 elements also with 0. And also you can keep this list here empty. If you just have an open curly parenthesis followed by a closed curly parenthesis, then you basically just initialize all elements with 0. Okay, so this is the situation for this array A. The variable ptr1 or pointer1 might have this memory location, and it gets initialized with the address of the first element. So it's pointing to this memory location here. Then you see that I'm printing out here certain values at the end of a pointer. I'm dereferencing this pointer. Here I'm considering the value of ptr1 plus 0, which is just ptr1, and then I look at the end of this pointer. So this here refers to this memory location. So this should print out 65. Then here I'm looking at the end of ptr1 incremented by 1. Now that means we increment it in our understanding by the size of 1 integer. So it will print out this memory location, 66. And here we will print out this memory location. So you see, when we add a 0 or a 1 or a 2, it has the same meaning as the index of the corresponding array element, because we actually use the size of an integer here for the unit that actually is used for the incrementation. Now with that in mind, it makes sense to introduce a new notation that you can use together with pointers for referring to values at the end of a pointer. You see that in this example, ptr1 is still a pointer to an integer. It's not an array, but I'm using here this notation for referring to array elements. But the compiler knows that ptr1 is actually a pointer. What the compiler does when it actually sees these expressions is the following. The compiler treats it equivalently to adding a 0 to ptr1, which of course would be the same as just ptr1, and then looking at the end of this pointer, dereferencing this pointer. So basically what you saw before. And the same here. If you have this ptr1 followed by a bracket with index 1, this is treated as if you would have written asterisk open parenthesis ptr1 plus 1, and here the same as before. This is equivalent to dereferencing ptr1 plus 2. So just the same. But still, don't get confused. Pointers and arrays are different. Again, consider how things look like in memory. We have here a0 followed by a1 followed by a2 with some initial values. So this here is variable a. And here we have ptr1. The size of ptr1 would be 8 on my machine, and probably also on yours. The size of a would be 3 times 4. So that would be 12. So a pointer and an array have a similar notation that can be used for referring to certain elements in memory, but they are different. So they have something in common, but they are not the same. I often say that the compiler is doing bookkeeping for us, and in this example I want to point out what this actually means. You see that this part here is basically the example from before, and in this second part you almost see the same, except that variables are called different and the types are different. We have an array of characters and a pointer to a character. But this part where we access these elements is the same in both cases. Now, what is it that the compiler keeps track of? If we visualize this here in memory, we see the picture basically from before. We have some memory locations for the array elements. So this, for example, for A0, A1, and this for A2, initialized with 65, 66, and 0. Then we have this memory location for ptr1, initialized with the address of the first array element, so it's pointing to this memory location. And the compiler knows that the size of this pointer is 8 bytes. The size of each element is 4 bytes. So we have here 4, 4, and 4. And with that, the compiler knows what it actually means that we, for example, access this memory location, that we actually access here. Let's do this in green. For example, this memory location. It knows that it has to increment the value stored in ptr1 by 4, and then to look into this memory cells that belong to this memory location with this address. Down here, the situation in memory for this array B and this ptr2 looks very similar. We also have a memory location for B0, here for B1 and B2. They are also initialized with 65, 66, and 0. and we have a memory location for PTR2. Now, the compiler knows that, again, the pointer has the same size as before, because all pointers are just storing addresses, and the size of an address depends on the platform, but not on what the pointer is pointing to. The size of each memory location here is 1, because these are characters. So this is the bookkeeping that the compiler is doing when it's generating code. And again, here, this PTR2 points to the first array element. And that means that, for example, here, the compiler knows that actually the value of PTR2 should be, in this case, just be incremented by 1, and then the dereference value would be this memory location. So this is the bookkeeping that the compiler is doing for us. And when you do assembly programming, you have to do this bookkeeping by yourself. And then, of course, you will understand or appreciate the bookkeeping done by a tool like a compiler. The compiler also can do bookkeeping in form of looking up ASCII values, what I'm doing here. If you use single quotes together with single characters, then the compiler is replacing it with the corresponding ASCII values. And the ASCII value for an uppercase A is 65, and for an uppercase B, 66. And of course, the same happens here, 65 and 66. So you generate exactly the same code from some different source code. But maybe the source code in this form, where you have actually these characters written out in single quotes, is more meaningful to you, and the compiler is doing the dirty job of looking up the ASCII values. You also can use this notation, which in this case also would generate the same code. But here you have a slight difference. If you have a string literal, then the compiler treats it equivalent to an open curly parenthesis followed by the single characters in single quotes. But now comes the difference with an additional terminating 0. So in this case, this string with 2 letters is equivalent to an initializer list with 3 elements, which in this case would have the same effect. You still would have the same code generated. But let's assume that you change the dimension here to 2, then the compiler can generate an error that you actually try to store 3 elements in an array with 2 elements. And this is in particular meaningful in this case, because a string is just an array of characters. And important is that strings are required to be 0 terminated. So often a frequent mistake is that you try to store a string with 2 characters in an array with 2 characters. And that's why here this error message generated from the compiler is actually helping you. So the bookkeeping, again, is helping us. In the exercises, we will also deal with something called type conversion. And these type conversions come in 2 flavors. There are implicit type conversions and explicit type conversions. And what you see in this example are so-called implicit type conversions. And those type conversions happen here and here. You see that before I, for example, had here on the right-hand side the address of the first array element, and the same here. Now let's first look at this code and understand that actually this cannot be right unless something is going on behind the scenes. Let's compare the left and right-hand side of this initialization. On the left-hand side, we have a pointer variable. So if we look at these things in memory, we have a memory location for PTR1, and we now know that the size of this memory location is 8 bytes. On the right-hand side, we have this variable A, which is an array of 3 integer elements. And each integer requires on my machine 4 bytes. We have 3 of them, so in total we have 12 bytes. So this assignment or this initialization cannot be right. We try to assign 12 bytes to 8 bytes. Doesn't work. But what is actually going on here is some convention. The compiler either could say this is not allowed because we are basically comparing here apples with oranges, or it could say, in this case, it has a certain meaning and I treat it differently. And in this case, actually, this is what is going on. If you write, in this case, on the right-hand side A, but on the left-hand side, you expect an address, then in this case, A is treated as the address of the first array element. So it's treated as if you would have written %A bracket 0. And this here is the implicit conversion or implicit cast. And the same is actually going on here. Here, in this case, B is treated as the address of the first array element. Also an implicit cast. And sometimes this is very confusing because this again suggests that arrays and pointers are the same, which is not the case. But if you know that these implicit casts happen, then it's very useful because it's a more compact notation. In this last example, I again want to point out what arrays and pointers have in common and what is actually the difference. You see that I'm having in function main 2 local variables. str1 is an array with 3 characters and str2 a pointer to a character. Now let's again look into the details, the memory situation after we entered function main. For this first variable, a memory location for str1 gets allocated with 3 bytes. Let's say this here, so we have 3 bytes. And the first byte, the first array element, gets initialized with 65 for the ASCII value of an uppercase A. The second with the ASCII value of an uppercase B or 66. And the third with 0. So this is the meaning of this first initialization of an array. If we now look at the second, then actually a lot more is going on. Let's draw this part of the memory here. We have a pointer to a character. That means we have a memory location that can store an address. So this would be 8 bytes. And this memory location gets initialized with a pointer to an array with 3 elements. Let's actually draw this array here in blue. So again, this would be 3 bytes. The first byte would have the ASCII value of C or 67. The second, the ASCII value of D. And the last 0. And what actually is going on is that the compiler generated a global array with 3 characters. So you can think of it as follows, that we would have here actually something like that, global foo or some internally generated name for an array of type array with 3 elements of jar initialized with the string cd. And here we actually could think of the compiler simply plugs in the internally generated name. And with that, this str2 can be initialized with the address of this first character in this string, with the address of this uppercase C, or the ASCII value of this uppercase C. So that's it for this video. In the exercises, we will actually deal a bit more with strings and how to understand what is going on behind the scenes.